dot products of vectors. So the definition of a dot product is if I have u, so vector u and vector v, if I am multiplying them, and we use a dot to show that we are multiplying them, you are really just multiplying the horizontal components, so u1 and v1, multiplying the vertical components, u2 and v2, but you are actually adding them. So whenever you do a dot product or multiply two vectors, you actually end up with a scalar, or just a number, as your answer. Below that, I have the properties of dot products written out. Now to make it fit on here, I went ahead and just typed them in, but I will go through them, pause as you need to so that you can copy them down. For all of these, u, v, and w are vectors, and c is a scalar, which you should be able to tell by whether they are bolded or not. So if I said the dot product of u and v, like u times v, that is the same as doing v times u. The order there does not matter. The second one, if I do the dot product of a vector and itself, so u times u, that is equal to the magnitude squared. And we'll do an example with that one in a minute. If I have my 0 vector, so 0, 0, multiplied by another vector, my answer is just going to be 0. It's your 0 property. Number 4 is basically your distributive property. So if you have vector u being multiplied by both that sum of v and w, then you're distributing the u to vector v and the u to vector w. Or vice versa. Ooh, looks like I missed a letter right here. Vector w there at the end of that. If I had the w on the outside, or the end, it still distributes. And then number 5 says that if I have some number times a vector, so cu, multiplied by another vector, I could really put that scalar with vector v. Or I could put the two vectors together and then multiply by the scalar. It's your associative property. Just like associative property of multiplication, it's the same with your dot product. So I'm going to ask you to find the dot product of each of these. I'm going to work through number 1, then I would say pause it, try the next 2, and then check in with what I get. So I'm going to do 4 times 2, which is 8, 5 times 3, which is 15, and then I'm adding them. And I get 23. Go ahead and pause now and try 2 and 3. So I got 0 and -6 for those respectively. Number 4, I've given you vectors u, v, and w. I don't want you to find each dot product. So it doesn't matter on 4 which order I go in. We saw that with one of the properties above. But I would just go ahead and start with u times v. So this, let me just get my numbers filled in. -1, 3 times 2, -4. And then I'm going to do that times vector w, which is 1, -2. So on my dot product here, -1 times 2 is -2. 3 times -4 is -12. I'm adding those to get -14. So now I have a scalar times this vector, so I am just distributing that -14. So I have -14, 28. I did end up with a vector as my answer because a vector times a vector gave me a scalar. A scalar times a vector, like we saw in the first stage, is still just a vector. On 5, go ahead and try this. I would start by probably distributing that 2. So I'm going to have -1, 3, still have my little dot product, but now I'm multiplying it by 4, -8. And And then negative 1 times 4 is negative 4. 3 times negative 8 is negative 24. Adding those to get negative 28. 6 says that the dot product of u with itself, so let me write that down, if u times u, okay, is 5, what is the length of u? So this is that property number 2 up above where it says the dot product of a number in its, or vector in itself is that magnitude squared. So I know that this is equal to my magnitude of u squared, which means that my magnitude of u is just going to be the square root of 5. For the angle between two vectors, we do have a formula for that. So that says that, let me zoom in just a little bit. If theta is the angle between, I'll zoom back out so you can see all this in a second. The non-zero vectors, so if you had the vector 0, that's not going in any direction, u and w. So if theta is the angle between the non-zero vectors and w, then cosine of theta is equal to my dot product, u times v, over my magnitude of u times my magnitude of v, which means that my calculator, I'm really going to be doing cosine inverse. So theta equals cosine inverse. And again, it is your dot product of u and v over the magnitude of u and v multiplied. So on number 7, I'm looking for the angle between vector u and v. You need to start by finding your dot product and your magnitude of both of those vectors. So I'm actually going to do it right here so I can still see the vectors. Let's see. U times v, 4 times 3 is 12, 3 times 5 is 15, I'm adding those to get 27. My magnitude of u is going to be the square root of 4 squared plus 3 squared, which is just 5. My magnitude of v is going to be the square root of 3 squared plus 5 squared, which 3 squared is 9 and 5 squared is 25, so I'm looking at radical 34. So I have to do all that work up front. Then I can plug them into this formula up here. So theta equals cosine inverse. Then on top I'm going to have my dot product. And my denominator I'm going to have 5 times radical 34. And then I'm going to type all of that into my calculator, making sure that I am in degree mode. And I'm getting that theta is about 22.2 degrees. For angles, I tend to just do one decimal. So 22.2 degrees. Alright, last thing, orthogonal vectors. The vectors, first off, orthogonal vectors really just means that they're perpendicular, or that they make a right angle. So if I have the vectors u and V, they are orthogonal if only if U times V, or my dot product, equals 0. So I know that the two vectors are orthogonal, or they have an angle between them that's 90, or they make a right angle, if their dot product is 0. And the reason for that is if you were doing cosine inverse of something with 0 over just any other number, that is going to be cosine inverse of 0, where cosine inverse of 0, only coming from the top, is going to be right at that top spot of 90 degrees. So my angle between them would be 90 degrees. That just has a special name, kind of like if two lines make a right angle, we call them perpendicular. If two vectors make a right angle or have an angle between them at 90, we call them orthogonal. So if I ask, are these orthogonal, you don't have to do all the work to do your cosine inverse and see if the angle between them is 90. All you need to do is your dot product. So 2 times 6 is 12. Negative 3 times 4 is negative 12. When I add those, I get 0. So yes, U and V are orthogonal.